Welcome back to the course. And today, what we'll be doing is we'll be looking at a quick summary of the different kinds of potential flows which we have. So, we'll look at certain already derived equations of the potential and stream functions for different streamlines, and we'll try and analyze them too. So first of all, let's actually, let's say we have a uniform streamline. So we have fluid particles flowing in one single direction. And let's say this is in 3D space. So the particles can have a velocity in the x direction. Let's say the velocity in the x direction is represented as u. Velocity in the y direction is represented as v. And velocity in the z direction, let's say, is represented as w. All right. And for now, let's just simplify our problem and let's just take the case for two-dimensional flow, and therefore I'm going to ignore the velocity in the z direction. So now we have the velocity in the x direction as u and in the y direction as y. And from this, I can write the potential function. I can, of course, just guess the potential function. We should get a potential function such that its gradient will give us the velocity equation. The velocity equation will of course be ui cap plus vj cap, and yes, you guessed it right. We have the potential function as ux plus vy. So this is the potential function which we have, and using what we learned last class, if we have a potential function, we can derive the stream function as well. So the the stream function which we'll get for this will be ui minus vx. So these are the two functions which we have. And another property about the stream and potential function is that they are orthogonal to each other. So for example, this is the stream function which we have. Then the velocity potential will be perpendicular to the stream. So now let's, instead of going on and deriving the rest of the streamlines which can be possible, so they are derived basically using the all the equations which we have: Navier-Stokes continuity equation and the potential and stream function conditions. So we derive them, and let me just actually present a table down. So here we have the summary of simple potential flows. Just a second. There we have it. So this is a summary of the simple potential flows which we have. Let me see if I can maximize it. All right. So as you can see in this flow, we just saw the uniform flow, and uniform flow is nothing but a straight line, and you get the potential as u infinity x or ux plus vy plus wz. So this is what we have, and we have the respective stream function as well. And similarly, if you have a sink or source, you'll have these kinds of streamline, that is water emerging from a point source. This you can think of a pipe. Let's say this is a pipe here and water is emerging in all directions. So that is kind of a source. Or else if you have your basin, and basin has a hole into it where all the water flows downwards or drains downwards. So that is known as a sink. So that is what we have. And therefore for a two-dimensional source or sink, we have the potential function as this. I think this is pretty small, so let me see if I can enlarge it more, even more. Yeah, I think that will be better now. So what do we have? So we have, for the source string, it is m by 2 pi ln x minus x naught square plus y minus y naught the whole square. So your m denotes the source strength. So m denotes the source strength, or in fact it denotes the flux coming out of the source, the strength of the flux coming out of the source, and m represents the source strength. So it's just the flux calculation. And in a similar way, you have other things. So here we don't have a streamline diagram for a 3D source sink because it's a two-dimensional paper, so we can't really represent that. Then we have for a vortex as well. So this is the potential and stream function for a vortex. Similarly for a 2D dipole and 3D dipole. And the special part about these functions is that you can actually use the principle of superposition. You must have heard this a lot. Principle of superposition to get different kinds of shapes and bodies to simulate. For example, here I have another table here. So this table, as you can see, if I consider a streamline plus a source, what I get is known as a Rankine half body. So it will look something like this. Rankine half body, and you have different kinds of flows going around this body. So if you superpose a stream and a source, you'll get such kind of a streamline. Similar way, if you superimpose a stream plus a source plus a sink, you'll get a Rankine closed body, which will look something like this. So if you superimpose a stream and a dipole, which we just saw above, this is a dipole. So if you superimpose a stream and a dipole, you'll get something like a circle. It looks something like this. The flow around it will look something like this. All right. And so on. So you have different kinds of superimpositions which you can do. And from this, finally, we can go on to discuss about aerodynamic or even hydrodynamic lifts and about drags. So that is a little math intensive, but it's also similar to this. So we do a little bit manipulations in lift. We see what a Kutta condition is, which causes or which promotes the lifting. So if you must have seen an aerofoil structure, it looks something like a teardrop, right? So you have all the streamlines coming here, all the streamlines flowing, and there is this Kutta condition, which I'm not telling what that now is. So due to that Kutta condition and other pressure differences, there is a net lift, and therefore your airplane flies. This of course you can apply in marine as well to design slender what do you say, slender shapes, so that you have less drag and more lift, or in fact more speed, and so on. So for drag and lift, I have two really nice YouTube videos. They explain it very well, and in an animated fashion, so that it's more you can just visualize it more better. And to see the mathematical side of it, I'm attaching the MIT Open Courseware link as well, so you can find all the lecture notes which I have referred to make these in that site. And also you can refer for real fluids. So this all we have talked about ideal fluids, right? Now we can also talk about real fluids, wherein the drag will come in and other kinds of effects will come in. So those notes are really they have explained it very well, and the mathematics behind it as well. So for a more mathematic intensive feel, you can refer those notes as well, which we'll attach it. So that's it for this course from my side. So we just saw a lot. We derived the Navier-Stokes equation. We saw what is streamline, path line, Eulerian, Lagrangian, and we are left with only lift and drag, which you can find out from the YouTube videos. So that's it. So thanks for watching and stay safe.